Have you ever thought about how many lives we could save if we could predict disasters before they happen? Diving right in, let's explore the concept of an early warning system. Like a well-oiled chain of interconnected parts, an early warning system comprises of information communication systems, sensors, event detection, and decision subsystems. Its noble purpose? To forecast disturbances that could negatively impact our world and provide us with the time to prepare and minimize the impact. Now, imagine a soldier on a battlefield. The soldier's strength lies not just in his physical prowess, but also in his ability to strategize, to anticipate the enemy's moves. Similarly, the strength of an early warning system lies not merely in its technological aspects, but also in the human elements that support it. Community involvement, public education, alert dissemination, and constant preparedness. These are the pillars that hold up an effective early warning system. They are the strategists on our battlefield against disasters. With their help, the system can support four main functions: risk analysis, monitoring and warning, dissemination and communication, and response capability. Early warning systems are our defense against various threats. They detect missile attacks, predict natural disasters, prevent pandemics, manage climate change risks, and even prioritize chemicals for regulatory interventions. They're our guardians, our watchmen, keeping a vigilant eye on the horizon for potential threats. The importance of early warning systems was brought into sharp focus following the tragic Indian Ocean tsunami in 2004. Since then, interest in developing these systems has soared, as we've recognized their potential to save thousands of lives. In essence, an early warning system is our shield, our armor against the unpredictable forces of nature. It's our way of trying to preempt the chaos, to stay one step ahead of the game. The power of early warning systems in disaster management is undeniable. But can we improve these systems even further? Let's explore that in the next scene. Enter the McGinty Equation, a mathematical model with the potential to revolutionize early warning systems. Now, this isn't your everyday arithmetic, but bear with me as we unravel its components. At the heart of the McGinty equation, we find two key elements: the solution of the free quantum field theory and the fractal potential term. Let's start with the quantum field theory. This is a branch of physics that combines the principles of quantum mechanics and field theory. It's like taking the unpredictable and often counterintuitive world of quantum particles and blending it with the classical understanding of fields like gravity and electromagnetism. In the McGinty equation, we denote this as piece QFT xt. Next, we have the fractal potential term. Fractals are complex geometric figures where similar patterns recur at progressively smaller scales. They're found everywhere in nature, from snowflakes to mountain ranges. In our equation, this is represented as fractal xtdmqs. Now, a simplified version of the McGinty equation combines these two components. But wait, there's more. A modified version introduces an additional element: the perturbative effects of gravity on the quantum field, represented as scravity xtg. This term signifies how gravity, the force that keeps our feet on the ground, interacts with quantum fields. Lastly, the fractal potential term Vyt has a self-similar fractal structure. This is described by the constant parameters V0, L, and S. The fractal correction term can be derived using integral calculus, Laplace transform, and the convolution theorem. All these elements together form the McGinty equation, a mathematical model that combines the laws of quantum physics, the complexity of fractals, and the strength of gravity. A potent mix, wouldn't you say? Now, you might be wondering, how can this equation help us in disaster management? Let's dive deeper. The McGinty equation isn't just a mathematical curiosity, it has real-world applications, especially in the development of early warning systems. Imagine if we could forecast catastrophic events like earthquakes and volcanic eruptions, potentially saving thousands of lives. This is where the McGinty equation comes into play. The equation, in its simplest form, is represented as piece xt equals sign psqft xt plus pes fractal xtdmqs. Here, piece qft xt is the solution of the free quantum field theory, a cornerstone of modern physics, and pes fractal xtdmqs represents the fractal potential term. Now, what makes this equation particularly intriguing for early warning systems is the fractal potential term. It has a self-similar fractal structure, which means it's a geometric shape that can be split into parts, each of which is a reduced scale copy of the whole. In essence, it's a pattern that repeats itself. This is significant because many natural phenomena exhibit fractal behavior. Think of the branching pattern of a tree or a river network. Earthquakes and volcanic eruptions, too, show fractal patterns in their occurrence. This is where the McGinty equation's fractal structure comes into play. By analyzing these repeating patterns, it may be possible to predict when and where the next branch, or in this case, the next disaster, might occur. But the McGinty equation doesn't stop there. It also includes a gravity term, represented as gravity xtg, which accounts for the perturbative effects of gravity on the quantum field. This term can be crucial in understanding the gravitational forces at play during seismic activities, giving us even more insight into potential disaster prediction. Incorporating the McGinty equation into early warning systems could revolutionize how we predict and respond to natural disasters. It's not just about knowing that a disaster might occur, but potentially understanding when and where it might happen, allowing for more effective disaster mitigation and potentially saving countless lives. With the McGinty equation, the future of disaster prediction and early warning systems looks promising. So, let's recap everything we've just discussed. We started off by highlighting the crucial role of early warning systems in disaster management, their functions, and their application in predicting various catastrophic events. We then dove into the intricate world of the McGinty equation, unraveling its components and exploring how they interact. We discovered that the equation's strength lies in its ability to represent the perturbative effects of gravity on the quantum field and its self-similar fractal structure. In essence, it's a mathematical model that can predict the unpredictable. We also explored the potential of integrating the McGinty equation into early warning systems. This could lead to a revolution in disaster management, enhancing our predictive capabilities and enabling us to react more effectively to impending disasters. And remember, the equation isn't just an abstract concept, but a practical tool with real-world implications. The McGinty equation could be a game changer in disaster management, potentially saving thousands of lives. It's a testament to the power of mathematics and its applications in the real world.